Earth, we owe our lives to the magnetic field surrounding our planet. Without it, charged particles from the sun would crash right into our atmosphere and whisk parts of it off into space. Fortunately, Earth's magnetic field fends off most of those particles before they can do any harm. But magnetic fields don't always play the hero. Other planets' relationships with their magnetic fields are complicated, and sometimes magnetic fields do more harm than good. For example, it seems like Mars has had it pretty rough. As barren as it is today, we can tell by its ancient canyons and dried out riverbeds that about 3.5 billion years ago, water flowed on the surface of Mars. And that would only have been possible if it had a thick atmosphere, putting enough pressure on the water to keep it in liquid form. But today, its atmosphere is super thin, less than 1% as thick as Earth's, which raises the question, where did it go? Researchers think the answer could have to do with its magnetic field. Satellite observations of magnetized rock formations on Mars suggest that around the time water was flowing on its surface, convection in its core created what's called a dynamo effect, a magnetic field set up by the swirling motion of molten metal. The magnetic field would have surrounded the planet and protected its atmosphere just like ours does on Earth. But for reasons scientists don't fully understand yet, Mars's dynamo effect stopped around 3.9 billion years ago and switched off its global magnetic field. And just like that, Mars's main protection against the sun's charged particles, or solar wind, vanished. But that wasn't the end of the story. Even now, satellites can still detect some very weak magnetism in patches of Mars's surface. That's because over time, Mars's global magnetic field had magnetized rocks on its surface. Those rocks held onto the magnetism baked into them even when the dynamo effect disappeared. And as a result of the magnetization in those rocks, Mars still has a weak magnetic field today. But you might think, a weak magnetic field, that's better than none when it comes to protecting an atmosphere. But in early 2020, a study in the Journal of Geophysical Research suggested exactly the opposite. The authors used computer models to predict how quickly Mars's atmosphere would have escaped from under a strong magnetic field, a weak one, or none at all. As expected, in the model with no magnetic field, the solar wind gradually swept the atmosphere away over time, while a strong magnetic field protected the atmosphere. But the fastest loss actually happened in the model with a weak magnetic field. See, on Mars, the magnetic field lines are so flimsy that instead of surrounding the planet like they do here on Earth, the solar wind bends them away from the planet like streamers blowing in the wind. This creates a sort of magnetic tail on Mars's downwind side. Unfortunately, that doesn't just channel charged particles from the solar wind. Charged particles from the atmosphere can also drift along magnetic field lines. The researchers' computer model showed that oxygen and carbon dioxide ions escaped through the magnetic tail faster than in the scenario with no magnetic field at all. And they believe that process is what sped up the loss of Mars's atmosphere and turned the planet into the barren world it is today. So for Mars, a bit of magnetism was a dangerous thing. But that's not always the case. Like on Mercury, a weak magnetic field is the whole reason the planet has any kind of atmosphere at all. The planet is pretty small, only about 1.5 times the size of our moon, and its gravity isn't strong enough to hold onto a proper atmosphere. But it actually does have some gases surrounding it. They're really sparse, and the atmospheric pressure is so low that we can't even measure it. But spacecraft have confirmed that there are traces of gas on the planet, and that's kind of odd. Given Mercury's weak gravity, even that wispy atmosphere should have drifted off into space a long time ago. So the only reason it exists today is because there's a process replenishing that gas over time. And that has to do with Mercury's magnetic field. Even though at the surface, it's only about 1% as strong as Earth's, Mercury's magnetic field is able to deflect some of the solar wind. But it can get a little patchy. And from time to time, its magnetic field lines twist up to form a little bundle called a magnetic tornado. These funnels twist out into space, and passing particles from the solar wind spiral down them, then crash into the rocky surface of Mercury at about 500 kilometers per second. That's fast enough to blast atoms off the surface and replenish some of the particles in its atmosphere. In fact, without its leaky magnetic field, Mercury might not have an atmosphere at all. So depending on the circumstances, weak magnetic fields can play both offense and defense for a planet's atmosphere. So now you might be thinking that strong magnetic fields would be more reliable protectors of their planets. But that's not always the case. When it comes to planetary magnetic fields, Jupiter is the solar system's undisputed champion. Even though its core isn't made of molten metals like the rocky planets, Jupiter's immense gravity creates a liquid core of hydrogen at its center, and that generates a powerful dynamo effect. In fact, its magnetic field is about 200 times bigger than the planet itself. That's about 20 times bigger than the sun. That gigantic magnetic field steers the solar wind well clear of Jupiter, millions of kilometers upwind from the planet itself. But on Jupiter's dark side, from time to time, that same field delivers a hidden attack on the atmosphere. See, despite its strength, the field doesn't form a perfect sphere around the planet. Instead, as the solar wind blows into it, the side facing the sun gets a little squashed, while the other side gets pulled along with the solar wind, giving the planet a long magnetic tail. In 2007, the New Horizons spacecraft flew through this tail on its way to Pluto, and it found something odd. There were blobs of charged gas particles floating down the tail like bubbles being blown in the wind. And scientists think those bubbles are a sign that Jupiter's tail is attacking its own atmosphere. They seem to form when the magnetic field lines stretching out from the planet reconnect with each other and create closed magnetic loops called plasmoids. Unfortunately for Jupiter, plasmoids can trap chunks of Jupiter's atmosphere inside, kind of like how a soap bubble traps air inside as it forms. Then those plasmoids drift off down the tail, swept along with the solar wind. Researchers estimate that this process could be whittling away Jupiter's atmosphere at a rate of 100 kilograms a second. In fact, plasmoids are stealing bubbles of gases from many planets, including all the other gas giants in our solar system. So no matter how strong they are, magnetic fields can have a sly streak. Now, not every planet generates its own magnetic field, but that doesn't necessarily mean that they're off the hook. Take Venus. There's no dynamo effect going on inside the planet, so you might think that it would be safe from plasmoids, but also wide open to attack from solar wind. And incredibly, neither one is true. When UV light from the sun hits Venus, it ejects electrons from atoms in its upper atmosphere, and that creates a buffer of charged molecules called the ionosphere. Then, when the solar wind collides with this ionosphere, it induces a magnetic field around the planet. That's because anytime you have moving charged particles, they create a magnetic field. So the particles in the solar wind carry a magnetic field of their own. But it also works the other way around. A magnetic field also moves charged particles. So the magnetic field from the solar wind moves the particles in the ionosphere. And when the particles in the ionosphere move, they then generate their own magnetic field. That induced field pushes back in the opposite direction to the original one that created it. For Venus, that means that the field in the ionosphere pushes back against the solar wind, just like an ordinary magnetic field would. And it actually protects Venus just like a normal one would too. But it also comes with its own problems. Like Jupiter, Venus has a long magnetic tail from its induced field. And occasionally, those field lines reconnect, forming plasmoids that snip away parts of its atmosphere, just like on Jupiter. With all the chaos taking place in the atmospheres around the solar system, at least here on Earth, our magnetic field is on our side, except when it's not. One of the most beautiful effects of our own magnetic field are auroras, also known as the northern and southern lights. These natural light shows happen when our magnetic field whisks particles from the solar wind toward our planet's poles. As they accelerate, they radiate light in the visible spectrum, creating those gorgeous, colorful streaks. But as pretty as they are, those particles don't always sail harmlessly through the sky. Sometimes they crash straight into oxygen ions in the upper atmosphere. When that happens, they often lose their energy and transfer it to the oxygen ion instead, speeding it up enough that it can escape the atmosphere and ride Earth's very own magnetic tail off into space. And that happens more often than you'd think. Earth loses 90 metric tons of its atmosphere every day to processes like these. But while 90 tons sounds like a lot, Earth's atmosphere contains 5 quadrillion metric tons of gas. That's a 5 with 15 zeros after it. So even 90 tons every day isn't going to make a dent for billions of years. And by then, Earth will probably have lots of other problems to deal with. So despite the little bit of leakage from our own precious atmosphere, we can still rest easy knowing our sturdy dynamo-powered magnetic field is keeping us safe. And from what we see around the solar system, there's definitely no place like home. Thanks for watching this episode of SciShow Space. And if you want to find out more about our solar system's fickle magnetic fields, you might like our episode about why Earth's magnetic field keeps flipping. You can watch that right after this.